Section 1 Introduction. In the past few years, transformers have taken the lead in the field of neural network architecture, particularly in natural language modeling tasks. This is due to their adaptability and their ability to be trained on extremely large datasets. These neural networks are often referred to as large language models, LLMs, with large indicating both the size of the training dataset and the number of parameters in the model, as well as the associated training and environmental costs. One of the key features of the standard transformer architecture is that it doesn't care about the order of the input elements. This is because attention, a key component of transformers, operates like a set, where the position of elements doesn't matter. However, the order of elements is crucial for many tasks such as natural language parsing, coding, forecasting, and more. Therefore, it's necessary to include positional information in the inputs of the LLM, usually in the form of positional encodings. One desirable feature of a positional encoding scheme is the ability to use the LLM for inference on input lengths longer than those it was trained on, a concept known as context length extrapolation. Due to the attention mechanism's quadratic complexity growth in transformers, it's often not feasible to train on large context lengths. However, increasing the context length can have various benefits, such as allowing the reading of longer documents and papers, maintaining internal consistency in long conversations with LLM-powered chatbots, working on larger codebases, and more. Context length extrapolation can be divided into two main approaches. The first is fine-tuned extrapolation, where a model previously trained on shorter contexts is allowed to fine-tune, or update its weights based on the longer context length. The second is zero-shot extrapolation, where a model previously trained on short contexts is immediately evaluated on longer context lengths using the same weights as the shorter context model. In this paper, we survey methods for context length extrapolation with a pre-trained base model and introduce a few of our own methods as well. We present a new truncated basis for position encodings. Unlike other works in the literature, which tend to train from scratch with a chosen positional encoding scheme, our focus is on pre-trained models. Training LLMs is a costly process, and the resources required to train competitive base models will likely remain limited to a few large players. Therefore, it's crucial to be able to modify the models as needed for the end user, ideally with a fraction of the compute power applied. Our main findings are that linear interpolation is the best method for context length extrapolation. However, all context length extrapolation methods show a decrease in task accuracy, even for lengths where they provide otherwise coherent output. Further context length increase can be achieved by using a higher scale factor at evaluation time than fine-tune time, but seemingly only up to a factor of 2x. We are releasing the weights of two new 13B models trained from base llama with an extended context length of 16K and a context length of 4K on Hugging Face. We also release a 13B model trained to a length of 32K from base llama. We call this family of models Giraffe. Additionally, we release three datasets, LongChat-Lines, Free-Form QA, and Altered Numeric QA, to evaluate the long context performance of these and other models. LongChat-Lines is a key-value fine-grained retrieval task. Free-Form QA and Altered QA are question-answering datasets based on the natural questions dataset. Some existing work focuses only on perplexity on a document corpus evaluation set as their measure of extrapolation performance. We find that perplexity scores are not as sensitive a measure of long context performance as our introduced tasks. In this work, we examine the efficacy of the positional encoding choice of llama for context lengths longer than the base model was trained on. The positional encoding used by llama is ROPE, rotary position embedding. ROPE works by rotating slices of the query and key projection matrices at different speeds. This means that even if the query and key are projected to the same encoding, they will be rotated by different amounts depending on their position in the sequence. If they are subsequently unaligned, their dot product will be smaller relative to what it would be if they were not rotated at all. Conversely, they could become more aligned, leading to a larger dot product and attention score. In ROPE, this rotation is happening at different speeds on all two slices of the query and key in the embedding dimension, allowing the model to build a complex function of attention scores over distances. One of the main appeals of using the ROPE method is that it ensures mathematically that the attention score function is dependent only on the relative distance between a query and a key, rather than their absolute positions. This is considered to be a desirable property of LLMs. Section summary. Transformers have become popular in natural language modeling tasks due to their flexibility and ability to handle large datasets. However, the standard transformer architecture lacks sensitivity to the ordering of input elements, which is crucial for tasks like natural language parsing and coding. To address this, positional encodings are used to inject positional information into the inputs. This paper explores different methods for context-length extrapolation in pre-trained models and introduces a new truncated basis for position encodings. The findings suggest that linear interpolation is the best method for context-length extrapolation, but all methods show degradation in task accuracy. The release of pre-trained models and evaluation datasets is also announced. Section: ALiBi. Let's delve into the world of ALiBi, rope, XPath, and other techniques used for context-length extrapolation in language models. Rope, or rotary positional encoding, was a significant step forward, but it had its limitations. The ALiBi study revealed that rope struggled with zero-shot context-length extrapolation, meaning it couldn't handle context lengths longer than what it had seen during training. ALiBi, on the other hand, introduced an alternative approach that performed better on their benchmarks. However, ALiBi isn't perfect either. It uses simple linear functions to modulate attention scores over distance, which limits its ability to represent complex distance attention functions compared to rope's Fourier basis. Moreover, ALiBi uses only one such function per head, which further reduces its expressive power. This might be why models using ALiBi perform worse than rope-based models on benchmarks like MMLU and the LMSY's arena, which measure human preferences. Sun et al. Explored why rope struggles with extrapolation and found that high-frequency components cause residual noise in the attention score, even when tokens are far apart. They proposed a solution called XPath, which adds an exponentially decaying amplitude term to rope. This method reduces the noisy high-frequency components faster than the low-frequency ones. XPath showed promising results in training language models from scratch, but Sun et al. Didn't test it in our area of interest, seeing if a model pre-trained with rope could learn the XPath encoding through limited fine-tuning. Another technique is linear scaling, positional interpolation, a simple yet effective method for context-length extrapolation. This technique involves dividing the position vector by a scaling factor to fit the input within the context length of the original model. The idea is to leverage the language model's interpolation capability, rather than relying on extrapolation. This method is known to avoid the risk of massive numerical explosion in attention values associated with extrapolation. Randomized positional encodings is another method presented by Roos et al. During training, they randomly generate their position vector by drawing samples from a range and sorting them in increasing order. This method reportedly improves performance on context-length extrapolation. We also explored a similar idea, but with some variations, which we'll discuss later. Now, let's talk about how we assess long context extrapolation. The common metric used is perplexity, but it's somewhat coarse-grained for evaluating how well the model can use longer context windows. We believe that a model can achieve a reasonable perplexity score even if it's only attending to information in a limited range. To get a more accurate assessment, we look at the model's accuracy when presented with problems that have verifiable answers. This way, we can evaluate how the model uses additional contextual information to respond to prompts. We use two types of evaluation tasks: key value retrieval tasks and question answering tasks. These tasks require the model to attend to the full context to obtain high accuracies. The retrieval task is a pure test of information retrieval, while the question answering task replicates more real-world tasks. Section summary. The ALiBi paper demonstrated that rope, a positional encoding method, fails to perform well on context lengths longer than what it was trained on. To address this, Sun et al. Proposed XPath, a new method that decays noisy high-frequency components in the attention score, resulting in better extrapolation. Another technique called linear scaling, positional interpolation, divides the position vector by a scaling factor to fit the input within the original model's context length, leveraging the model's interpolation capability. Randomized positional encodings, introduced by Roos et al., randomly generate position vectors during training and achieve improved performance on context-length extrapolation. The paper evaluates the effectiveness of these techniques using key value retrieval and question answering tasks, which require the model to attend to the full context for accurate results. Section: LongChat-Lines. We'll begin by discussing a synthetic fine-grained key value retrieval task that was first introduced in previous studies. While these studies are commendable, they don't fully address the need for longer context lengths in our experiments. So, we've decided to use the same task but with additional samples that have longer context lengths. In this task, the model is given a prompt with lines like, line grotesque classmate, register_content is 42,527 inches, or, line imperfect bull, register_content is 3,119. The model's job is to remember the value associated with the register_content for each line. Then, it's asked to retrieve the value for a specific line. By changing the number of lines in the prompt, we can control the context length. We've released longer versions of this task and the script used to generate it. We've also created 2 new datasets from the natural questions dataset, specifically designed for longer context evaluations. We call these WikiQA. In these evaluations, the model is given a Wikipedia document and a question related to that document. The model's task is to answer the question. We ensure that the answer is a short word or sentence that matches exactly with the text in the document. We call this task Free-Form QA, FFQA. However, there's a potential issue with this Wikipedia-based dataset. The model might answer correctly using its pre-trained corpus, not the context information. To address this, we've created another dataset, which we call Altered Numeric QA, ALT-QA. This dataset only includes questions with numerical answers. We've changed the answer and every mention of the answer in the document to a different number. This ensures that the model must use the context to answer correctly. If the answer is a year, between 1000 to 2100, we change it to a random value within plus or minus 10 of the original value. If the answer is any other number, we change it to a random number with the same number of digits. We've done this to maintain the document's overall coherence. Since our contexts are long, the answer's location within the context could significantly impact the model's ability to answer the question. So, we use both WikiQA tasks to analyze the model's performance as the answer location moves within the document and as the question is given at the beginning or the end of the prompt. Next, we'll discuss several context length extrapolation techniques, including existing methods and our newly proposed ones. Existing techniques include linear scaling, positional interpolation, where the position vector is divided by a scaling factor. For example, if the original model was trained on positions from 0 to 2048, the new model will see positions from 0x to 2048x, where x is the scaling factor. We also evaluated the XPOS technique, which involves fine-tuning the base model's rope encoding scheme to the XPOS scheme. However, this method is sensitive to floating point precision and requires patching the entire attention module to handle XPO's unique transformation of keys and queries. To overcome this, we performed the core attention operation in float 32, which slowed down training by 2x. Another technique is randomized position encodings, where we randomize the distances between the position values uniformly in the range from epsilon to 2, rather than using fixed intervals of size 1. The idea is that by showing the model many different intra-position distances at fine-tuning time, it will be able to generalize to any choice of fine-grained positions at evaluation time, allowing for an effective increase in context length. We set an upper bound of 2 and a positive, non-zero lower bound of epsilon to avoid issues with position aliasing due to limited numerical precision. Section Summary. The section describes the tasks and datasets used to evaluate the performance of the language model. One task involves retrieving values based on prompts with varying context lengths, while another task involves answering questions based on Wikipedia documents. To ensure that the model relies on the context rather than pre-trained knowledge, a modified dataset with altered numerical answers is also created. The section also discusses different techniques for extrapolating context length, including linear scaling, XPOS encoding, and randomized position encodings. Section: Power scaling. Let's delve into the topic of power scaling. In the original rope model, we use a specific mathematical basis, which we'll call theta. This basis is calculated using a formula that involves the embedding dimension, represented by the letter d. However, we decided to tweak this a bit and use a different basis, which we'll call theta star. This new basis is calculated using a similar formula, but with an additional parameter, k. This change affects the elements of the basis differently based on their frequency. High-frequency elements, which correspond to short distances, are less impacted than low-frequency elements, which correspond to long distances. The latter are made even lower in frequency. Our aim with this change was to simplify the model's task of extrapolating for low frequencies, where it hasn't seen the full range of the periodic function during training. However, we also noticed a potential issue. The model might rely on specific relationships across frequencies that a linear transformation preserves, but a nonlinear transformation might disrupt. Next, we introduced the concept of a truncated basis. Here, we use a different basis, theta star I, which is calculated based on certain conditions. If theta I is greater than or equal to a certain value, b, we use theta I. If theta I is between a and b, we use a fixed value, rho. If theta star I is less than or equal to a, we use 0. The idea behind this is to keep the high-frequency components of the basis intact, but set the low-frequency elements to a constant value, in this case, 0. We believe that this approach, combined with a careful choice of the cutoff A, will help the model extrapolate better to larger context lengths for evaluation. We also include the fixed frequency, rho, to help the model distinguish between distances that span the entire context it was trained on. Our hope is that this new basis will help the model avoid the need to learn complicated coefficients in the entire rope basis, and instead learn smooth functions at longer distances. We then conducted experiments using a base Llama 13b model, which we fine-tuned on a portion of the red pajama dataset. Each data sample in this dataset has exactly 4,096 tokens. We trained the model using each positional encoding approach until the evaluation loss roughly plateaued. We also applied instruction fine-tuning, IFT, using the Vicuña dataset and LoRa on the base model. However, we found that while IFT did boost accuracies on LongChat-Lines, it didn't significantly change the range of contexts that the base model could handle. This was a stark contrast to the WikiQA variants, where IFT was necessary for the model to produce any meaningful results. We conducted evaluations on LongChat-Lines using the techniques described earlier and reported the results. We expected all models to perform with a non-zero accuracy until at least 4,200, given that the model is fine-tuned on context lengths of 4,096 and convergence is achieved in all cases. However, this wasn't the case for XPOS, which couldn't perform the task at all. We suspect this might be because XPOS is too different from the rope basis for the model to adapt during fine-tuning. This might also be due to numerical precision issues encountered in the implementation of XPOS. Linear scaling, on the other hand, was able to achieve successful context length extrapolation. However, we noticed a quicker degradation as context length increases with a scaling factor of 16. By context length 17,500, it was already recording 0% accuracy, even though we expected reasonable performance up to roughly 32,000 context length. The power basis performed best at the shortest context but decayed fastest and couldn't show any extrapolation performance beyond 4,200 context at all. The randomized position approach seemed to be extrapolating based on the results, but this was likely due to how we evaluated the model. The truncated basis seemed to offer true context length extrapolation, as it was able to achieve non-zero accuracies on context lengths outside any values it has seen before. Although the performance does degrade as the length increases, we believe that this may be a direction of investigation that can lead to better extrapolation performance. Truncation can also be combined with linear scaling for potentially better results. Section Summary. In this section, the authors propose two modifications to the original rope basis used in the model. The first modification involves a power scaling transformation that affects the low-frequency elements of the basis more than the high-frequency elements, aiming to improve extrapolation for low frequencies. The second modification is a truncated basis, where the low-frequency elements are set to a constant value while preserving the high-frequency components. This modification allows the model to better extrapolate to larger context lengths. Experimental results show that the truncated basis performs better in achieving context length extrapolation compared to other approaches. Section: WikiQA variants. We've conducted further evaluations on the WikiQA variants, as mentioned in a previous section, using linear scaling and truncated basis methods. We discovered that without fine-tuning the instructions, the models couldn't perform the task successfully. Therefore, we only analyzed a few interesting approaches. The results, shown in tables and largely follow the pattern seen in LongChat-Lines. With a scale factor of 4, linear scaling can perform the task up to a context of 7,500, but not beyond. A scale factor of 16 can surpass this limit, but with a decrease in accuracy. As with LongChat-Lines, we noticed a slight decrease in accuracy as the context length increases. The truncated basis method can successfully extrapolate to about the same context length as in LongChat-Lines, with similar accuracies to linear scaling with a scale factor of 4. However, it seems unable to go beyond a context length of about 8,000. In the previous section, we looked at the performance of linear scaling using the same value at fine-tuning time as at evaluation time. Now, we're investigating the effect of using a different scaling factor at evaluation time than what the model was trained on. We found that if the model is trained with a scale factor of x, it can successfully evaluate zero-shot with a scale factor of 2x, although with some reduction in accuracy. However, at a scale factor of 16, the model can't increase its effective context length using this approach. Evaluating with a scale factor greater than 2x causes the model to fail at performing the task. Interestingly, While using a longer scale factor at evaluation time results in a decrease in accuracy on context lengths the model could previously handle, this doesn't seem to be the case for the truncated basis. Instead, the range of context lengths that the model achieves non-zero accuracy on increases, and accuracy improves among context lengths the model was fine-tuned on. We introduced two tasks in section that require a long context language model to extract answers from the entire text. We argued that these tasks may assess long context performance better than raw perplexity. To analyze how perplexity compares to these tasks, we reported perplexities on a held-out set of the red pajama dataset for a subset of our trained models. Perplexity scores do show a large increase when a context length is reached that the model can't handle. However, they are less effective for showing the decrease in long context capability within that effective range. We also noticed that perplexity falls short for between-model comparisons. According to the table, the truncated basis performs best at 8,000 and below. However, in other tables, it is significantly lower in performance compared to the linear scaled models at 8,000 context. Perplexity is commonly used to measure long context performance, but we believe these results show it is not a sufficient measure of long context performance on its own. It is best used with other tasks that also probe the capabilities of the language model. For the WikiQA variance, we analyzed the effect of the position of the answer in the question. We looked at the impact of placing the answer within the first 10% of the document, the last 10%, or elsewhere randomly. We also examined the effect of putting the question at the beginning or the end of the prompt. The results, performed on the model with linear scaling with a factor of 16, with additional instruction fine-tuning, showed no clear trend with regards to the location of the answer within the prompt and the model's accuracy up to 15,000 context length. However, at 24,000 and 32,000 context lengths, we see a clear indication in both datasets for both the answer at the end and question at the end returning superior accuracy to their placements elsewhere. These results are a marked contrast to those in. Our takeaway from this is that there is likely a great deal of task-dependent variability in the performance of language models with regards to how well they can utilize all portions of the context. Even small differences in task construction can lead to large differences in observed trends.